In section 4.1, we look at inverse functions. So here is the definition of an inverse function. Let f be a function. A function g is said to be the inverse function of f if the domain of g is equal to the range of f, and for every x in the domain of f, and for every y in the domain of g, g of y equals x if and only if f of x equals y. The notation for the inverse function of f is f inverse, so it looks like a little -1 exponent, but that's not an exponent. Equivalently, we say f inverse of y equals x if and only if f of x is equal to y. And again, the notation f -1 does not mean 1 over f, it means the inverse function. Okay, that's a lot to take in. Let's go ahead and try to understand this a little bit better. So here is basically what is happening when you have an inverse function. First of all, let's recognize that this is a set of numbers, and we will call this set of numbers the domain of f. That is the set of all numbers x that we can plug into the function f. When you plug a number x into the function f, the function will take that number and assign to it a number that we call f of x. Now keep in mind that we also call this number f of x y, right? So f is taking the value of x and sending it to the value that we call y. So what the inverse function does is it will take this number over here, which is the number y, and it will send it back to where it came from. So we say f inverse of y is equal to x. Now this set over here is what we call the range of f. And that is the set of numbers that you get from the function f. And so the inverse will take any number that is in that range of f and it will send it back to the domain of f where it came from. So in a real simplistic way, an inverse function will simply undo whatever the function does. Now, to try to understand this a little bit better, we're going to talk about the composition of a function and its inverse. So again, keep in mind that the function will take this number x and we'll send it over to this number f of x, which we also call y. And basically the idea is whatever this function does, the inverse function is going to undo it. And so in that regard, the two functions cancel each other out. So for every x in the domain of the function f, if you apply the inverse function to the f of x, you are going to get x. And for every x in the domain of f inverse, if you apply the function to the inverse function of x, you are also going to get x. So when either one of these functions acts upon the other function, it cancels it out. To help us understand the definition of an inverse function, let's consider the following example. Here we want to verify that the following functions are inverses of each other. We have the function f of x equals 3x minus 4, and g of x equals x over 3 plus 4 over 3. Before we verify that these are inverses, let's consider a simple example. Here we have the domain of the function f, and the number 5 is in that domain. The function f will take the number 5 and assign it to a value in the range of f. Let's compute what that value is. So to do f of 5, we're going to plug the number 5 into the function here, which is 3x minus 4. So if we do that, we get 3 times 5 minus 4, which is 15 take away 4, which equals 11. So the function f takes the number 5 and assigns it to the number f of 5, which we know is equal to 11. Now, if the function g is actually the inverse, then what it should do is it should take the number over here, which is 11, and it should send it back to the number 5. So in other words, if g is the inverse, it should do this. Let's see if that happens. What do we get if we plug the number 11 into the function g? Well, g of 11 is 11 over 3 plus 4 over 3. Now, if we do the math on that, 11 plus 4 is 15, and we have our common denominator of 3. And 15 divided by 3 indeed is 5. So I want you to see that the number 5 gets assigned to the number 11 in the original function, and in the inverse function, the number 11 gets assigned to the number 5. So you see, these functions simply undo each other. So you can see that in their ordered pairs. If we were graphing these functions, the point 5, 11 would be on the function f, and the point 11, 5 would be on the function g. So one thing that inverse functions do is they interchange the x and y values. Now let's go ahead and verify that these are actually inverses of each other. Now you might be thinking that we've already done that, but that's actually not true. All we have shown is that the number 5 gets assigned to 11, and then the function g will undo that number. But to be inverses, it has to do that for every single value of x that we can possibly plug in. And so we can't prove it in this way because we would have to plug in infinitely many numbers to show this. So instead, we're going to rely on compositions to do this for us. If these functions are truly inverses of each other, then when we plug the function g into the function f, we should get x. Also, when we plug the function f into the function g, we should get x. Let's verify that each one of these actually happens. So we'll start with doing f of g of x. Now this is f of the function g, and the function g is x over 3 plus 4 over 3. Now, f of this function means that we are going to take this function here and plug it into the function f. So that's going to be 3 multiplied by x over 3 plus 4 over 3 minus 4. Now we just need to simplify. If we distribute the 3 here, we get 3 times x over 3, which is x. And then we have 3 times 4 thirds, which is positive 4. And then we have the negative 4 here. And you can see that this is indeed x after these two terms here cancel out. Now let's check to see if it happens the other way. So when we plug the function f of x into the function g of x, we get g of 3x minus 4, right? Because we're now plugging this function f into the function g. Now, when you put 3x minus 4 into the function g, we replace the x in function g with 3x minus 4. So we have 3x minus 4 over 3 plus 4 over 3. Since we have a common denominator, we can combine these together by adding the numerators. So we have 3x minus 4 plus 4 all over 3. Again, these two terms here cancel out, and we end up getting 3x over 3, and finally the 3's also cancel out, and we end up with x. So what this means is that when you apply one function after the other function has already been applied, basically these two functions are canceling each other out, and you're just getting the number that you had here. And if you do it in the other direction, these cancel each other out as well. So that is what is meant by inverse functions. So next we need to talk about how to find the inverse of a function. So in this example, let's suppose we have the function f of x equals negative 2x plus 3. And we want to find its inverse. And here we have some steps for doing that. So the first thing we're going to do is write down the function that we have, which is f of x equals negative 2x plus 3. Then what we want to do is replace f of x with the variable y. So this equation simply becomes y equals negative 2x plus 3. Now the reason we're doing this is because when you have an inverse function, it is going to invert x and y. So the x and y simply get switched. And that's the third step. Interchange the variables x and y so that the input variable for the inverse function is x and the output variable is y. So y becomes x and x becomes y. And now what we're going to do is solve for the new y. To solve for y here, we are going to subtract 3 from both sides. When we do this, we get x minus 3 is equal to negative 2y. And then to solve for y, we're going to divide by negative 2 on both sides. And when we do that, the negative 2 cancels out. And we end up getting x minus 3 divided by negative 2 is equal to y. Now we can clean this up just a little bit. If I multiply the top and bottom by negative 1, and the reason I'm doing this is because we really don't want to have a negative in the bottom of a fraction. So negative 1 times negative 2 gives us positive 2. And in the numerator, when you multiply by negative 1, you have to distribute that to each of these terms. So that's going to be negative x and positive 3. Now, once you've solved for y and simplified, this new y value is your inverse function. So our inverse function is y equals negative x plus 3 divided by 2. And all we're going to do now is change y to the inverse function notation, which is that f inverse of x notation. And so what we have in the end here is the inverse function of f of x is the function negative x plus 3 divided by 2. And again, the way we usually say this is we'll say f inverse of x. So next, what I want to do is talk a little bit more about the theory of inverse functions. To do this, we need to define what is called a one-to-one function. For a function f to have an inverse, the function must be one-to-one. And what it means to be one-to-one is that f of a equals f of b only if a is equal to b. Now, to determine whether a function is one-to-one, you could do it sometimes algebraically by looking at what we have here, but it is easier to understand this from a graphical point of view. The way we do this is by using something called the horizontal line test. The horizontal line test tells you that when you have a one-to-one function, every horizontal line intersects the graph at most one time. So if you look at this function right here, this function is not one-to-one. And the reason it's not one-to-one is because when you draw a horizontal line, you can see that it intersects the graph of the function here, and it also intersects the graph of the function here. And if you think of this as being A and this as being B, we can see that f of A is equal to f of B, right? Because they have the same height, the same y value. However, A is not equal to B because clearly these two numbers are different on the x-axis. So if f of A equals f of B and A and B are not the same, you do not have a one-to-one function. So again, the easy way to think about this is that if you can draw a horizontal line that hits the graph more than once, it is not one-to-one. So an example of a function that is one-to-one would be a function that looks like this. Now notice that every possible horizontal line that you draw here only hits the graph of the function one time, right? Every horizontal line that you draw. So this function is one-to-one. So let's take a quick look at an example about one-to-one functions. Determine which of the following are one-to-one. So our first example here is the function f of t equals negative 3t plus 1. Now, we don't have a graph of that, but we can take the definition of that function and determine if it is one-to-one. So if f of t equals negative 3t plus 1, then think about what would it mean for f of a to be equal to f of b. Well, f of a is negative 3 times a plus 1, and f of b would be negative 3 times b plus 1. And if f of a equals f of b, notice that if we subtract 1 from both sides, we end up getting negative 3a is equal to negative 3b. And then if you divide both sides by negative 3, you can see that this must mean that a is equal to b. So again, if f of a equals f of b, and a must be equal to b for this to be true, then it is a one-to-one function. And by the way, 1-1 is an abbreviation for 1-to-1. So yes, this first function is one-to-one. Now if you look at part B here, the function given by this graph, is this a one-to-one function or is it not a one-to-one function? Well, they don't give us an algebraic equation for this, but we can see by the graph very clearly that if you draw a horizontal line, you are going to hit the graph more than one time. In fact, this particular horizontal line hits the graph 3 times. So this one is actually really simple. This is not one-to-one. And finally, for the last example, it says to look at the function f given by the values in table 2. So here's our table, and we want to know, is this a one-to-one function? So what we're looking for is f of a equals f of b. And if you look carefully here, you'll notice that the function value here is 0, and the function value here is 0. So from that table, I can see very clearly that f of negative 1 is equal to 0, and also f of 5 is equal to 0. So we can see very clearly that f of negative 1 is equal to f of 5. However, negative 1 is not equal to 5. Therefore, this function is not one-to-one, right? Because the basic idea is that you have two different x values that give you the same y value. And that means basically if you were to graph this function, those two different x values would give you the same y value, which means a horizontal line would hit the graph more than once. Now let's talk about the relationship between the graph of a function and the graph of its inverse. So we know that the graphs of a function f and its inverse function f inverse are symmetric with respect to the line y equals x. What exactly does that mean? Well, what we want to do here is graph the function f of x equals negative 2x plus 3, and also its inverse function f inverse of x equals negative 1/2 x plus 3 over 2. And we're going to graph these on the same set of axes, using the same scale for both axes. So what that means is that you want your x-axis and your y-axis to have the same scale. Let's go ahead and take a look at those graphs, and then we'll see the symmetry that we should see. Now both of these functions are lines. The function negative 2x plus 3 is given by this graph right here. The function negative 1/2 x plus 3 over 2 is given by this function here. Now, if you draw the line y equals x, which is this line right here, you'll notice that these functions are mirror images of each other across that line. So you can see that on the function f, there is a point here at negative 1, positive 5, and on the function f inverse, there is a mirror image of that point directly across that line, and the coordinates of that point are 5, negative 1. So notice that the coordinates negative 1, 5 have simply been reversed to the coordinates 5, negative 1. And when you do that, you get symmetry directly across that line. So again, if you just go straight across the line y equals x, perpendicular to that line, you'll see that these 2 points are mirror images of each other. And another example of this, if you look at the point here on the inverse function, which has coordinates -3, +3, there is a corresponding point on the original function, +3, -3. And these 2 points are also mirror images of each other directly through the line y equals x. So anytime you have 2 functions that are both 1-to-1, that are inverses of each other, you will have this graphical symmetry. For our next example, let's consider the function f of x equals x cubed plus 1. We want to show that f is 1-to-1 using the horizontal line test. So to do this, let's take a look at the graph of the function. So here's what the function looks like in a graph. Now, you can take the time to graph this function by plugging in some x values and y values, but we just want to get straight to the point here. Notice that every possible horizontal line that you draw intersecting this graph will only intersect the graph 1 time. So yes, this function is 1-to-1. So we've completed part A. Now for part B, they want us to find the inverse of f. So to do this, let's remember how to find the inverse. So our function is f of x equals x cubed plus 1. The first thing we're going to do is change f of x to the variable y. After that, to find the inverse, we are going to interchange x and y. So y becomes x and x becomes y. After doing this step, we are now going to solve for y again. So to solve for y, I will subtract 1 from both sides here, which gives us x minus 1 is equal to y cubed. And then to solve for y, we need to cancel the cube. And to cancel a cube, you need to take a cube root. So we take the cube root of the left-hand side and the cube root of the right-hand side. And when we do this, we get the cube root of y cubed is y, and on the left-hand side, we have the cube root of x minus 1. And this is our inverse. So now we're just going to change the notation from y to f inverse of x equals the cube root of x minus 1. So this is our inverse function. Now for the third part, they want us to graph the function f and its inverse on the same set of axes. So let's bring in the graph of the inverse. So here's what the graph would look like. We have our original function f of x here. The inverse function cube root of x minus 1 is this function here. And for reference, I have the line y equals x, which comes right down the middle. You'll notice that these graphs here are perfect symmetrical images of each other across that line. So for example, notice that the function passes through the point 0, 1, and the inverse function passes through the point 1, 0. Another point to notice is the point 2, 9 is on the original function, while the point 9, 2 is on the inverse function. And again, those are symmetrical points because they go directly across that line y equals x, perpendicular to it. And in fact, every point that you have over here has a mirror image across that line and on the inverse. In our final example, we want to talk about restriction of a domain to find an inverse function. So the first thing we want to do is show that the function g of x equals x squared has an inverse. Now, how do we know when a function has an inverse? Well, we know a function has an inverse when it is 1-to-1. So what we need to do is we need to show that the function g of x equals x squared when x is greater than or equal to 0 is a 1-to-1 function. Well, what does g of x equal x squared look like? Let's take a look at its graph. So we know the function g of x equals x squared has the following points, right? When you plug in 2, 2 squared is 4. When you plug in 1, 1 squared is 1, etc. And if we graph those, we get the following. So we have the point 0, 0, 1, 1, 2, 4, negative 2, 4, and negative 1, 1. And we know that this is basically just a parabola. Now, that function is not one-to-one. So g of x equals x squared does not have an inverse because you can see here when you draw a horizontal line, you're going to hit the function twice. But remember, they told us x must be greater than or equal to 0. When they say x must be greater than or equal to 0, it means that we are not allowed to plug negative numbers into our function. And what that does is it erases the left-hand side of the graph. And so now the graph just looks like this. This is the function g of x equals x squared when x is greater than or equal to 0. Now we do have a one-to-one function. So since this function is one-to-one, because every possible horizontal line only hits the graph one time, we know it now has an inverse. So next they want us to find the inverse. So let's go ahead and go through that process. So to find the inverse, the first thing we do is we change g of x to be the variable y. So we have y is equal to x squared. Then what we do is we interchange x and y. So y becomes x and x becomes y. And from here, we are now going to solve for y again. To solve for y, we simply take the square root of both sides. Now, when you take the square root of both sides, you get y is equal to plus or minus the square root of x. But remember now, we were told in the beginning that x is greater than or equal to 0. So if x is greater than or equal to 0, when you interchange x and y, it means that y has to be greater than or equal to 0. And if y is greater than or equal to 0, then that means that we cannot have the plus or minus here. So y is only equal to the square root of x. This is our inverse. So the inverse function here is going to be g inverse of x is equal to the square root of x. Now, just to make sure that we understand that this is the inverse, let's do its graph. So let's get a few points. I'll make a horizontal table here. I'm going to plug in x equals 0, 1, and 4. Well, the square root of 0 is 0, the square root of 1 is 1, and the square root of 4 is 2. So if I graph those 3 points, we have the point 0, 0, 1, 1, and 4, 2. And its graph looks like this. And you can see that this inverse function indeed appears to be the mirror image of the original function. And in fact, if we graph the line y equals x, right down the middle here, you will see indeed that we have that symmetry that we expect to have when talking about inverse functions.